Okay, so now that we've covered convexity of functions, we're going to come to the lecture that you've all been waiting for, which is gradient descent. How does this magical, crazy algorithm work that seems to be used in every kind of optimization problem everywhere? And it's true. The algorithm we're going to talk about today forms the basis of optimization, machine learning. Kind of a lot of the advances that you're seeing today are based on gradient descent. Not all of the algorithms, in fact, none of them are running exactly gradient descent, right? Gradient descent is the first algorithm, and then there's like 3,000 different variations on it, and 3,000 is probably an underestimate. And depending on your specific application, you will choose exactly which one is most relevant. The most commonly used one is probably stochastic gradient descent, which is a common variant, which we'll talk about as well. But what we're going to do is we're going to delve into the details of gradient descent so that you can understand in depth why this one algorithm works, which will then enable you to understand how all of these other algorithms work. It's kind of the same way that, ridge regression is a modification of least squares that allows you to go beyond what least squares does, right? And you can use it kind of to fine-tune least squares. Similarly, and least squares is the foundation, right? That's the first thing you learn. Gradient descent is that foundation for all algorithms, right? So fundamentally, oh, by the way, there's a midterm, just in case you forgot, and in case I forget, I wrote it on the board. But you should have all the information about it in your emails. Okay. So now, let's say we have some optimization problem, right? I want to minimize f naught of x subject to, let's say, x belongs to Rn. And my optimum value I'm going to call p star, right? This is an optimization problem. We've been talking about optimization problems like this for a while now. In an ideal world, all of my problems would be like least squares, where I say minimize something, right? What does least squares say? Minimize ax minus b norm squared. And then I get a formula for x. And I get my best x hat, right? Isn't that great? Turns out that that is almost never true in real life. You never get like a clean formula. Very rarely will you even get to prove that something is the optimal. What you're often doing is you're trying to search for the optimal. You're trying to say, how can I get as close to the optimal as possible? And so what gradient descent is it's a way to take something like this, which is an unconstrained optimization problem. So you'll notice that there's no constraints here. I'm not saying that, x must be less than 2 or x must be greater than 3 or whatever. X can be anything in Rn. And what this is saying is, let's say we were to play a game, right? So you pick an x, and I tell you the value of f of x, okay? So if we were to play this game back and forth, what is a principled way by which you might be able to get closer and closer to the minimum, right? So you've all played this game of 20 questions, right? For example, you say, okay, well, let's say I have a number in mind. And then you say, is it bigger than 20 or less than 20? And then I can tell you something, and then you say, oh, is it bigger than 10 or less than 10, right? Everyone knows this idea of how to find what a number is, right? And so this is kind of an example of an algorithm by which you can keep asking me questions and eventually come to the number that is in my head that I've hidden away. Gradient descent is kind of doing the same kind of thing, which is saying, well, currently this is where you're at. Tell me, what could I try next? What could I try next? What could I try next? And the idea is that hopefully you will eventually converge to the point that you want to get to. Does that make sense, everyone, for what we're going to try to do? Okay, good. So let's say, basically, I have my f of x. Let's just call this f of not f of okay. And now I know the value of f of x, let's say, at some point. And now I want to say, what's my next guess? I want to pick some f of x plus delta x, right? I told you what f of x is. And now I want to pick my next guess. And remember, what I'm trying to do is I'm trying to minimize my function, right? So I want to try and get as close to the minimum as possible. So if you knew f of x, what might you want to choose as delta x to try as your next guess, right? If x is your current guess, f of x plus delta x is going to be your next guess. The question is, how do you figure out what delta x is? Does everyone understand the question? OK. So when I write this expression here, what is the thing that you're tempted to do? What is the thing we know about f of x plus delta x? We want to compare it to f of x. What tool do we have that lets us do that? Taylor series, right? Taylor's theorem. So can I write this? How do I write this? I can write this as f of x, right? So I'm saying, how much different is this from f of x, right? Plus, I have my update, right? And then I have some other terms here. But let's just stick to these first few terms. OK? So how can I choose delta x? A standard way in which this is sometimes written, this is exactly the same thing. But I can write this as f of, instead of writing delta x, I can write this as s, which is a step size, and v, which is a direction. OK? Times s times v, right? Just saying delta x is equal to s times v. S is a scalar. So I want to minimize my function, right? If I want to minimize my function, do I want this thing to be greater than f of x or less than f of x? To get a better guess, I want this to be less than f of x, right? So this I know. I know the difference between this term and this term, between f of x and my next step. And it's given exactly by this. So do I want this thing to be positive or negative? I want this to be negative, right? Everyone see that? Yes? Everyone with me? OK, good. So now, can I write this term, gradient of f of x transpose times s times v? I can write this as s times gradient of f of x inner product with v, right? I'm just rewriting this. Nothing fancy there. But now let's look at this quantity. This is an inner product between two vectors, OK? So gradient of f of x is what it is. It's pointing in some direction, OK? And now I'm choosing a v. Let's just think of this in 2 dimensions, right? I'm choosing a v. And I want to now, do I want to maximize the inner product with gradient? Or do I want to minimize the inner product with the gradient? What do I want to do? S is positive. I want to make f of x plus delta x as small as I can, right? So I want to have v, do I want to have it in the direction of gradient, orthogonal to the gradient, opposite to the gradient? Right? What is the inequality that we know that connects inner products to, like, how do we, can we say something about inner products and angles, and what's that thing called? There's a midterm coming, in case that incentivizes you.
So cosine theta
Okay, so cosine theta plays a role. So now you have, what is this inner product? So you have this, just remember, right? So let me just write this here. What do I have? If I have two vectors A and B, what is their inner product equal to? Norm A, norm B times cosine theta, which is the angle between them, right? So now, what cosine thetas maximize this? When cosine theta is 1, this is maximized. When is this minimized? When cosine theta is -1, right? That's the minimum possible value of this inner product. So if I wanted to minimize this thing, what theta would you choose? You would choose 180 degrees, right? You would choose V to be pointing exactly in the opposite direction of the gradient. Does everyone see that? Yes? No? Questions? This is the key thing, right? You've got to get this. Does everyone understand what I'm saying? Yeah. Okay. So therefore, to minimize choose V so V basically you choose which brings you to gradient descent, right? Move in the direction opposite to the gradient to descend your function. Everyone see why this is the direction we choose? This is the relevant thing, right? It's not magic. There's nothing special or, you know, I mean, it's very special, but it's not magic, right? It's exactly, quantifiably, provably understandable, okay? Okay, so basically, what we always try to do is we always try to choose the next step of gradient descent in a way that we are moving in the direction of the negative gradient. So gradient descent is an iterative algorithm where, let's say, I'm currently I start at some initial vector x0, okay? Then I want to find my x1. How do I find my x1? Well, I say I want to take where I am at x0, and then I'm going to move a step size eta in the direction of the gradient at the point that I was just at. Does everyone see how this step is exactly mirroring what we just discussed was the optimal way to move? Right? Now I'm moving in the direction of the negative gradient. Everyone seemed fine up here, and now I'm seeing confused faces. What's happening? Ask me a question. Yes?
Is eta the step size?
Eta is the step size. Yeah, this is called eta. It's like an N with a tail, Greek letter. That's the standard notation that is somehow used for gradient descent step size. It's just every textbook, that's what you use.
Is it a scalar?
It is a scalar. Eta is a scalar. It is greater than 0, and it is a real number. In general, what you might write as the gradient descent algorithm is that xk is equal to xk, or maybe xk plus 1 is equal to xk minus eta times gradient of f at xk. Everyone with me? Questions? This is utterly obvious and boring? Okay, yes, I'm seeing confused faces, so I need you to ask me questions, otherwise I won't know what you're confused about.
So do you just use the same eta for every step of the iteration?
Wonderful. So the standard gradient descent algorithm always uses the same eta, okay? There are variations where you will adapt your step size, and we're going to see the role of the step size in just a minute. But choosing this step size correctly is extremely important, and we'll see exactly how that's important in maybe 10 more minutes. Yes, could you explain again why v equals a negative gradient of x? So I know what f of x plus delta x is, right? I want to figure out how delta x is how much I'm going to move from where I'm currently at. If I want to move, I'm going to say I want to move in the direction that makes my function smaller. If I want to make my function small, then that second term had better be negative. For that to be negative, that inner product had better be negative. The only way to make that inner product negative is to make sure that the gradient of f of x and v have a negative inner product. One way to guarantee that, in fact, the way to make that the smallest is to make sure that that cosine theta is negative 1. The goal is to try to get as close to the minimum of f of x as possible, right? F of x is just f of x I can evaluate at different points, and gives me different values, right? I'm trying to get to the min of f of x. I want to try to get to p star. Why does s have to be positive? Great question. S has to be positive because we're defining it that way, which allows us to make sure that we're taking a step in the negative gradient. Right? If we allowed s to be positive or negative, then if s is negative, we have to take a step in, like, you have to change your direction. This is an extra degree of freedom that we don't need. Right? Once you determine the direction, all you have to determine is the magnitude in that direction. Great question. The direction vector v, does it have to be a unit vector? This is an excellent question. So why am I not restricting v to be a unit vector? Well, eventually, right now I'm telling you this way of trying to make my function smaller, right? So with when we're playing 20 questions, you ask me a question, and you're trusting that when it's the right answer, right? Let's say the number I have in mind is 4, right? And if you say, is your number 4, you're going to trust that I'm going to say yes, right? Otherwise, a game of 20 questions doesn't work, right? You have to trust that the person playing the game is kind of being truthful with you. However, when you're running gradient descent, you're programming a computer. The computer is just saying, I'm currently at xk. I can go to xk plus 1. What is your stopping condition? How do you know when to stop this thing? When does the game end? Or do you just keep asking and asking and asking and asking? How do you know that you've gotten to the minimum, right? So what do we know about getting to the minimums and gradients? If the gradient is 0, then we know that we're at that's a necessary condition for being at a minimum, right? If it's a convex function, we know that that's the only point, right? Here we're not restricting to convex functions. We can do gradient descent on non-convex functions too. But if we happen to be in the lucky case where we're at a convex function and we find a gradient 0 point, what's going to happen when your gradient is 0 in this algorithm? Nice, right? You're not going to move. The algorithm is automatically going to know that you've reached the minimum. Okay? So here, one of the nice things is that we use the magnitude of the gradient. As the magnitude of your gradient is getting smaller and smaller, you're effectively taking smaller and smaller steps. Right? So as you're getting closer and closer to that 0 gradient, even if your eta, your step size is constant, the magnitude of that gradient is naturally decreasing, which is helping you get to this point. So that's one of the reasons that we don't restrict v to being a unit vector, because otherwise you would lose this natural property of the gradient, which is that it gets smaller as you get closer to your minimum. If you're at a maximum, your gradient is 0 at that point.
So it actually doesn't change anything, right?
Yeah, if you're at a local maximum, your gradient is 0, and the gradient descent will actually not move you.
So in that case, how do we fix that? Like if we actually choose it.
So there's a great question of how do you get out of local maxima and local minima, and we'll come to that. Okay, the question is, can you explain again this thing about the unit vector v? Okay, so let's say hypothetical other update. Okay, xk plus 1 is equal to xk minus eta times okay. So this is another hypothetical update rule that I could use, right? Am I moving in the direction of the negative gradient in this? I am, right? But the step size that I'm taking is changing, right? So now this thing, what is the magnitude of this? This is 1, right? So what is the size of the step that I take at every single time point? It's always eta, right? It doesn't change based on k, ever, okay? And so let's say my eta was set to be 5 or something like that. I'm coming very, very, very close to my optimum. How do I decide, if I'm, like, let's say I have some loss function. Okay, this is my minimum, let's say here. So this is my loss function, this is my minimum here. And I'm starting out here, okay? This is my x naught. So here, which way is this is my tangent line, right? And so which way is my negative gradient? My negative gradient is going to point me in this direction. I'm going to take a step like this, which will bring me here. Right? Here, then I'll take a step like this, which will bring me here. Now, if my step size is always eta, let's say this is eta, right? I'll come here. Oops, I overshot. Oops, I overshot by eta. Oops, I overshot by eta. Right? Whereas, if I have something where my step is naturally becoming smaller and smaller, instead, for example, if I was to do something where, oh, here I take this big step because I'm far away. Slightly better, smaller step. I take smaller and smaller steps as I come closer and closer to my minimum, I'm less likely to go ping-ponging overshooting, right? So the fact that the gradient naturally is becoming smaller and smaller here, right? The gradient is large here. But it's small. It's closer and closer to 0 the closer and closer I get to my minimum. So naturally, by having this, the distance between my xk and xk plus 1 and xk plus 2 becomes smaller and smaller and smaller by keeping this gradient as it is and not normalizing. Everyone see that? Did that answer the question? I forgot who asked the question, but yeah? Okay, great. The question is, we're only writing 2 terms of the Taylor equation. What about all of the higher order terms, right? You're just pretending that your function is this linear approximation. So the thing is that when you're choosing your delta x small enough, when you're close enough to your minimum, those higher order terms are going to be insignificant compared to the first order linear approximation.
So we can ensure that the delta x is quite small.
So the question is, does everyone understand the question? Like, because I don't know that you can hear it. But when I'm doing my Taylor series, what happens to the rest of the terms, right? And the rest of the terms, basically, are all going to have higher multiples of delta x, right? They're going to be delta x squared, delta x cubed, so on and so forth. When delta x is small, these are necessarily going to decay to 0 faster than delta x, right? So the dominant term is going to be that linear term. Therefore, this is a good approximation. There are, of course, algorithms that you can do, and we will talk about one of them, Newton's algorithm, that uses also the second order terms. But we're not there yet, so we will get there eventually. Okay, let's now do an example. So my f of x when you're learning something new, come back to something familiar and understand it in the case of something familiar. So what is actually argmin of this? How many people know how to compute the argmin of this function? Every single hand had better go up. Okay? Right? Everyone knows this? Least squares? We know how to do this? Great. Let's solve this now instead using gradient descent. Okay? So we know what this function is. You also know what the gradient of this function is. What is the gradient of this function? Now you've done it many, 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 many times. Yes? Wonderful, right? This is the gradient. And so let's say I start at some x naught. Okay, this is my initial condition. So now let me write xk plus 1 equal to xk minus eta times gradient of f of xk. Right? So what is the gradient of f of xk? Well, this is xk minus 2 eta times 2 A transpose A xk plus 2 A transpose B, or 2. Right, I just plugged the gradient into this equation. Everyone see what I did? So let's say I'm starting at some arbitrary point x naught. I'm trying to solve least squares. And what this is saying is that if you started at xk, the next point you should pick is given by this equation, according to gradient descent. Okay? So I can play with this a little bit, and I can write this as, this xk I can write here as an identity times xk, right? I put an identity matrix in front of this, no one cares? Okay, so this is identity minus 2 eta A transpose A xk plus 2 eta A transpose B. Right? So what kind of equation is this? It's now something that's giving me, xk plus 1 in terms of xk, right? It's a recursive update, right? Okay? So let's say I had something like this. Xk, if we were scalars, is equal to, or xk plus 1 is equal to 2xk plus 3. Okay? Let's say this is my update equation, just for some example thing. What is the limit of xk as k goes to infinity? What is this? What's going to happen to my xk every single time? It's doubling, right, approximately? So as k goes to infinity, what do I get? Very good. What if I had xk plus 1 is equal to 1/2 xk plus 3? What is the limit in this case? Great question. If x0 was negative, this could go to negative infinity. Yes, sorry, I'm assuming, let's say x0 is 1. Just good point, fair point. Point I wanted to make was just that it's diverging. Actually, no, even depends on what the value of x0 was, but yeah. This is going to converge to something, right? Is it going to be finite or infinite? It's going to be a finite thing. Okay, let's just do this. What if there was no 3 here? What is this going to converge to? 0, right? With the plus 3 here, this becomes a geometric series that you have to add up, right? Okay? Do you see that in one case you're clearly going to go to infinity, and the other case you're clearly going to be finite? What is the threshold for which determines whether you're going to go to infinity or whether you're going to stay finite? 1. If this coefficient is bigger than 1, you're going to blow up either to plus infinity or minus infinity. If this coefficient is less than 1, you're going to stay finite, right? And that exact finite value will depend on what that constant is. Yes? Everyone with me? Okay. So what is this equation here? There's some constant here. And here, instead of a number here, this is now a matrix, right? So what happens when I keep taking powers of this matrix, when I keep iterating this equation over and over again? What do I see? What determines, so if I have some matrix now, I have a matrix A, and let's say it's square. What determines what happens to the powers of this matrix? What is the quantity that matters? What are the quantities that matter? As you take powers of this matrix. You've all done this before. Definitely been on homework in this class. Eigenvalues and singular values, right? Okay, so when the eigenvalues are greater than 1, this thing blows up, right? When the eigenvalues are smaller than 1, this is going to stay bounded. What kind of matrix is this here? Identity is a symmetric matrix, right? A transpose A is a square symmetric matrix. What is identity minus 2 eta A transpose A? This is a symmetric matrix. What do we know for a symmetric matrix? So let's call this matrix Q. Q I can always write as what if Q is symmetric and square?
Diagonalizable.
It's diagonalizable. How can I write it? Some U lambda U transpose, right? Where these are the eigenvalues. Okay? And so Q to the K is equal to U lambda to the K U transpose, right? So now to determine whether xk plus 1 blows up or converges, what do I need to look at? The eigenvalues of this thing, right? Does everyone see that? Okay, so quantity of interest to determine if xk goes to infinity or not, eigenvalues of had better be, what do they need to be? What do the eigenvalues need to be? Less than 1, right? And I need to look at the absolute value of the eigenvalues. Right? Anything that's smaller than 1 is fine. If I had a negative 1/2 here, this would still be finite. What if it's equal to 1 is still finite? It's marginally stable, but yes. So how do the eigenvalues come into play, right? What is this equation, right? I have xk plus 1 is equal to some matrix Q times xk plus some other vector b. Right? Whether or not this is finite depends on the eigenvalues of the matrix Q. Because whether or not q times xk is going to be finite, how do I know what q times xk is going to be? What quantity determines that, right? This is now the 2 norm of this matrix Q.
Oh, it's like analogous to that.
It's exactly analogous to that, right? And even if it's exactly that, because q times xk, what is the maximum that it can blow up xk by? What is the 2 norm of q, right? We know that this is the singular value. If q is symmetric, this is just the eigenvalue, right? Everything coming together? Like we've been working on this towards this for a while now. Okay, everyone with me? Okay, good. So now we have some sense of what this matters. And I want you to notice here that I'm saying absolute value of the eigenvalues need to be less than 1. Right?
Is this for each eigenvalue? Or
Every single eigenvalue has to be less than 1 in absolute value. If you have even one eigenvalue that's going to be greater than 1 in absolute value, in that direction you will blow up. So this tells me whether or not, and for gradient descent, do I want to be blowing up or do I want to be converging? Like you can keep playing this 20 questions game, right? But you want it to end. Otherwise you'll be miserable. How do you know that gradient descent is going to end? Sometime, somewhere. You want to choose, you want to make sure that these eigenvalues have an absolute value less than 1. Right? Okay, so let's say you had that. How can you now figure out where this is going to converge to? Right? So now, say, assume okay? Where do we want this thing to converge to? Do you think it's going to converge to something different from our actual solution? What is our x star for this problem? We know x star, right? What is our optimum? Well, it's A transpose A inverse A transpose B, right? So let's see, how fast are we approaching this solution? So if I consider now xk plus 1 minus x star, right? I want to see how fast am I getting close to this. Does everyone see that that's the next natural thing that I want to do? How fast am I getting close to my actual solution? Okay. Well, this thing is equal to identity minus 2 eta A transpose A xk plus 2 eta A transpose B minus now A transpose A inverse A transpose B, right? Everyone with me? Okay. Now, is there something I can do to kind of like maybe massage this to look nicer? Yes?
Sorry, just to clarify,
we will now want to prove that basically what we want to show is that this xk converges to this x star, right? Which means that we want to show that this distance converges to 0. Everyone see that? So how could you do that? Maybe just actually take a minute and try to see if you can manipulate this to see how you might be able to do that. What might you want to be able to do? So remember, we want to be able to get, this is kind of our key matrix, right? So if we can get something, things that are easy to talk about convergence, if you want something to converge to 0, it's really great if you can get xk equal, xk plus 1 is equal to some constant alpha times xk, and this thing is less than 1, right? In the scalar case. So how can we do that? Can we manipulate this somehow to get that exact same thing here? So if I look at this terms over here, I have this A transpose B and A transpose B here in common, right? Okay. So I can write this as this term plus 2 eta minus A transpose A times A transpose B, right? Wouldn't it be so much nicer instead of here if I had something that looked kind of like this? Instead of 2 eta minus A transpose A, could I somehow make this look like that?
Wait, what about that
Oh, did I? Oh, sorry, this should be inverse, right? Sorry, yeah. And 2 eta should be multiplied by identity, correct. Thank you. So can I somehow manipulate this thing? Is there something else that I might want to pull out?
You factor out A transpose A inverse to get the same thing that you have on the left-hand side.
Can I factor this out? Okay, great. So what do I do?
2 eta A transpose A.
So I want to get out A transpose A inverse. And then I get here 2 eta A transpose A minus identity. Right? And I'm literally kind of pattern matching to make this work. And so if I just fill in what I have here, very convenient, right? So now this is equal to identity minus 2 eta A transpose A times xk minus A transpose A inverse A transpose B. Cool. So now if I keep taking powers of this, so can I iterate on this and can I say now this is equal to identity minus 2 eta A transpose A squared times xk minus 1 minus A transpose A inverse A transpose B. Just recursively plugging in this formula. Right? Can I keep going? Yes, question?
You have to flip the sign because over there it's I minus 2 eta.
Yeah, that's why I have a minus sign there.
Oh, okay, thank you.
Does everyone see this? So now as I keep going, and if I know that this thing has eigenvalues that are all smaller than 1, what is this matrix going to converge to? Right? This matrix is going to converge to 0. Does everyone see that? Therefore, what is x going to converge to? Exactly x star, right? As k goes to infinity, I'm going to converge exactly to A transpose A inverse A transpose B. OK, so if I have a matrix Q, OK? Let's say Q is equal to 1/2, 0, 0, 1/3. What is Q to the k as k goes to infinity? This is 1/2 to the k 0, 0, like this is 1/2 to the k 0, 0, 1/3 to the k, right? This is going to the 0 matrix, right? Does everyone see that? Yes, everyone with me? So this thing, as k goes to infinity, so now I did this for k minus 1. I can further write this as if I can keep writing this. I can write I minus 2 eta A transpose A. And if I put this to, I would have k plus 1 x naught minus A transpose A inverse A transpose B. Right, I just keep doing this 1 by 1 by 1 by 1 by 1, right? And I go all the way to my initial condition. So as k goes to infinity, what is this going to go to? This is going to go to the 0 matrix, right? And so here on my left-hand side, what do I have? I have xk plus 1 minus x star. Right? So this had better also be going to 0, which means that xk plus 1 is going to x star, and x star is exactly what I've defined it to be, right? It's exactly where I want it to converge. That is my minimum point. The question is that, well, you're thinking about this q to the k, for example, and this is not exactly 0, right? I'm just getting arbitrarily close to 0. I'm not ever actually at 0. And so how do I know that I've exactly gotten there, right? So what is happening is that every time step, you're getting a little closer, a little closer, a little closer, a little closer, a little closer. What will happen, though, is that if you hit a point where the gradient is actually 0, you will end up not moving because your gradient itself will be 0. So gradient descent can actually get you to the point. But in practice, often you might not get a gradient 0 point, right? And so in practice, what is often done is that you can put in stopping conditions to gradient descent. So what you do is you say that, let me look at the difference between xk and xk plus 1. And if the distance between my iterates is small enough, and you set a tolerance threshold, and if you get small enough, then you stop. Or you say, let me measure my gradient. If my gradient is smaller than some threshold, then I stop. So these are, in practice, the kinds of stopping rules that are implemented. So is the question of how did you get from this to this? OK, so the question is, how did I get from this to this? I have this is something in terms of xk. I'm iterating, and I'm just substituting the so I can write now this term xk, like by recursion, I can write xk minus this as this times this, but where I replace this k with a k minus 1, and that's all I've done, right? So I'm replacing this term by this times this replaced with a k minus 1. Like I'm just doing recursion. There's nothing but exact recursion. So look, what have I shown here? I have xk minus x star is equal to this thing times xk minus x star. Right? So I'm replacing that exact thing every time. Is there any relationship between the step size you choose in your Q matrix? Absolutely. So now the question is, I have to choose an eta here that guarantees that the eigenvalues of this thing are smaller than 1 in absolute value. If I choose an eta that does not guarantee that, I'm toasted completely, right? Because this thing is going to behave like 2 to the k or 10 to the k, right? The only place this behaves nicely is when these things are smaller than 1 in absolute value. So I have to choose an eta. Okay, so let me show you guys a demo. Maybe that will help also clear things up. Okay, so I'm trying to do a least squares problem. Okay, so let's say I have as my data, I want to fit this line. Ignore everything else. I just have these x's. This is my data. Everyone see how fitting this is? I just want to find the slope of this line. This is a one-dimensional least squares problem. Everyone see that? I'm not even trying to find the offset. I'm just trying to find the slope of this line. So if I set that up, I'm saying, like, let's say I have some data points. I have some true slope. In this case, I've chosen it to be a half. And I've taken some points, and I'm just trying to find what my y is. Right? I'm trying to find this true slope. Okay? And I have some noisy points here. Everyone see how this is a least squares problem? What is the loss is going to look like? It's a quadratic function, right? What this function here is the loss function for this. Okay? And now I'm going to try to solve this by doing gradient descent. So n is what I'm going to set as the number of steps I want to take. Okay? Eta, let's say I'm going to choose something. Let's choose something very small. Eta is my step size. And then let's say I run this. So what I'm plotting here is this is my loss function. This is my data. And I'm taking these tiny steps here up at the top. Everyone see that? 10 steps, I'm barely moving anywhere close to the minimum, right? So maybe instead of taking 10, let's say I take 1,000 steps. Wow. I'm still not getting anywhere, right? I'm barely getting. Does everyone see this? Maybe I should make this is too tiny even to illustrate. Let's just make this 0.1. Okay? So now my eta is 0.1, taking still pretty small steps. Now this thing will not render. Where do I want to get to? I want to get to here, where my gradient is 0, right? But clearly I'm not getting there. So what should I do now? What is the problem that I have? What other step size would I choose? I'm choosing a tiny step size, right? So I can either take more steps. And if I take more steps, I'm getting closer. But what's happening is that as I'm getting closer and closer, because my gradient is also getting smaller and smaller, my step is also getting smaller and smaller. And I'm not really getting there, right? I'm not overshooting, but I'm not getting to where I need to go. So what happens if I increase my step size? Let's, instead of say 0.1, let's make this 0.4, right? And let's take 100 steps. Oh, OK. I increase my step size. And now you can see when I'm far away, I'm taking these big steps. Big step, big step, big step. And now as I'm getting closer and closer and closer, I'm converging pretty fast to where I need to be. Does everyone see that? Well, maybe I can do better, right? Like, I don't want to be taking 100 steps. That's still kind of a crazy number of steps. Can I do it in less steps? What if I make less steps, but I increase my step size even more, right? Make it 0.5. Well, 0.5 is doing better, but I'm not quite getting there in 10 steps. What if I make this 0.7? Ah, not quite, but doing better. Maybe I can make this step size 1. Oh, 1 is basically almost getting me there, right? And you can see here basically for every gradient descent step, what is being plotted here, the green line is the best fit line corresponding to your first gradient descent update, then the second gradient descent update, then the third gradient descent update, so on and so forth. So as you kind of get better and better, you're getting better and better to the actual line. Does everyone see? Is what the demo is trying to do clear to everyone? Okay. So here I'm kind of getting there. Well, maybe let's make it even bigger, right? 2. Okay. 2 is getting me there pretty well, right? Could I do faster? What if I went to 5? Whoa. Right? I'm still converging, though. I'm still converging to where I want to be, but I'm doing this like giant ping-ponging now, right? Because my steps is so big every time that I'm really going everywhere. What if I made it 10? Well, now my gradients are so big they're not even being plotted, right? I have now reached the realm of divergence, right? Look, as you can see, I'm like not even, like my lines are all over the place. I'm not even trying to fit the data. Everything's kind of crazy. So let's see if I can get this to plot for maybe like, I think this 7. 7 is still too big. 6. Okay, this is a good figure, right? Basically, I'm completely diverging. Like I want a line to be here, but I'm keep guessing like over here and over here. I'm just ping-ponging from crazy slope to crazy slope, and I'm diverging, right? I'm not converging. So basically, if your step size is too large, you're toast. Does everyone see that? Yes?
Didn't we prove over there that no matter what the step size was, it would converge eventually?
No, what we proved over there is that if the eigenvalues of identity minus 2 eta A transpose A are smaller than 1 in absolute value, then you will converge.
So the case where the step size is too big corresponds
To when those eigenvalues are not smaller than 1 in absolute value. And you see what's happening here pictorially, right? You can do the same thing now for, let's say you have a 2-dimensional setup. Yeah, so I was playing with this before lecture. So here now, instead of, again, I have the same thing. I have a bunch of points to draw, I have a bunch of points to fit. But now I have a 2-dimensional setup because I want to learn the slope and the offset, right? So I have 2 parameters, theta 1 and theta 2, that I'm both trying to learn. Here I'm calling the step size alpha. And now, for example, if I choose my step size equal to 2 here, what's happening? I'm starting here, but I'm just completely overshooting my minimum here, right? The loss landscape here, now this is a least squares problem. The loss landscape is a hyperbola, right? It's like a cup in 3D space. So what is plotting here are the contour lines of that, right? This minimum point is here, and I have these ellipses that are corresponding to my norm ax minus b norm squared. But now if I choose something where, like, if I choose my step size equal to 1, and I start here, I'm kind of pretty fast converging to where I want to be, right? Whereas 2, you saw, was completely diverging, right? And so now you will do, this is exactly the homework problem that you have, is that given the eigenvalues of A transpose A, what is the largest eta that you can choose, right? What is the best eta that you want to choose? This clearly depends on what the eigenvalues of A transpose A are, right? You just want to choose things such that 1 minus 2 eta times the eigenvalue is smaller than 1 in absolute value. Right, so it's a simple inequality. You solve it, you get exactly what the best eta is, or what the range of possible etas is. Questions about this demo? Make sense to everyone? Does this help clarify what's going on with the math that we just did? Yeah? Okay. I can turn this off. No more questions?
What was going on with that second?
What was going on with that second plot? What do you mean?
I'm just a little bit confused about what it's representing, or how.
So what is this representing? So here, I have some data. These x's are my data. I'm doing a least squares fit of this data. My loss landscape, my cost function, is plotted here. When I have only 1 dimension, in this case, I have a parabola, right? But now, if I'm doing least squares in 2 dimensions, and my unknown, what I'm trying to find is a vector, what this is going to be in 2 dimensions is going to be a hyperbola, right? Or it's going to be, it's going to be like a big cup, right? And so what is being plotted here are the contours of that, which are going to look like ellipses, right? These are the, remember you did that homework with vector calculus where you had to plot the isocurves? These are the isocurves.
So the level sets.
The level sets, exactly. Everyone remember that homework problem? Okay, good. We're done. Can I move on?
If it's any value of the matrix closer to 0, then the quicker
how do you determine what is the fastest convergence? The things that will converge the fastest to 0 are basically dependent on the eigenvalues, right? So your rate is basically the largest eigenvalue raised. So that's basically going to determine your convergence rate. The question is, without actually seeing the plot, how do we know if our step size is right or wrong? You're going to know if our step size is right or wrong by looking at, you can compute the eigenvalues of exactly this. This is exactly the problem on your homework. And basically by checking if these are smaller than 1 or greater than 1 in absolute value, you can decide if things are going to converge or diverge. The question is, if it's too small, it doesn't work either. Great question. So what I showed you there was that when things were too small, it was taking a really long time to converge. Okay? That doesn't mean it won't converge. It just means it's converging at a very slow rate. Okay? So basically, if I have something that has a very small rate of decay, then it might take me 1,000 steps, 10,000 steps to get to 0. But I will eventually get there. So what you often want to do is you want to find that eta that is large enough that you will converge quickly, but not so large that you're going to overshoot. Because if you choose an eta that is too small, you will converge, but it'll just take forever. So now what remains is, for example, to say, well, for a question like least squares, would I ever do gradient descent in practice? When you have giant least squares problems that you're solving, why would I bother doing gradient descent? I already got a formula, right? We proved it. Why would I bother doing gradient descent? Would you ever bother doing gradient descent? Turns out that quite often in real life, you will not use this formula. You will actually do gradient descent. So why might that happen, right? So consider, what does it take to solve A transpose A inverse A transpose B? What does it take to kind of be able to do this? Let's say I had n equal to 10 to the 6 data points. Okay? To be able to do this, I need to do a matrix inversion, right? So if I have n data points, my A transpose A inverse is going to be about order n cubed, right? So I'm going to have an order n cubed inversion to do here at the minimum, right? And then on top of that, I have to do the matrix multiply, which is like relatively small. It's an n squared operation, right? So that's not really, and that's not being. But now, computing this gradient, right? What is the gradient that I have to compute? So my gradient of f of x is this thing, okay? To compute this gradient, what are the operations I have to do? Well, I can compute 2A transpose B. And that's kind of quick to compute, right? This is just a matrix multiply. This is an order n operation, n squared maybe. And then I have to compute this A transpose A, right? And this matrix multiply is how many operations? Also in the order of n squared operations, right? It's cheaper than an inversion. So now let's say I'm taking k steps, okay? So every time I compute a gradient, I have to do an order n squared operation. Let's say a transpose A if I've computed and kept in memory. But I have to do at least the A transpose A times x, right? That I have to do new every time. That's an order n squared operation. So if I do k steps, I have to do computation k times n squared, right? That's the order of the operations that I have to do. So if I have 10 to the 6 data points, how many operations can I afford? I can do 1,000 steps. So if I have 10 to the 6 cubed is what it takes for me to do my inversion here. But if I had k equal to, let's say, 10 to the 3, I can do 10 to the 3 times 10 to the 6 squared, and I will get my solution using gradient descent, right? So if I have a very, very large data set, it's actually faster for me computationally to find the solution using gradient descent than it is for me to do this massive matrix inversion. So for large data sets, that's actually what people do in practice, is that you might actually end up and the thing, that's why the name of the game is getting gradient descent to converge fast, right? You don't want a gradient descent where your step size is teeny tiny and it's taking you millions of steps to converge, right? That's why there's a lot of investment, like value in getting that to do fast. And that's why there's all these variations. There's variations where you don't compute the full gradient. Stochastic gradient descent is, for example, one example of that. You only compute basically a partial gradient. You will do things like you will adapt your step size. So you will artificially decrease eta. You won't keep eta constant, but you'll keep changing it so that you might converge faster. There's like a bajillion different variations. We'll talk about some of them in the next class. And what I want to talk about in the next class is also, we just proved this is true for one very specific example, right, which is least squares. What I want to do is I want to generalize that to talk about when does gradient descent converge in general for functions, okay? Gradient descent will provably converge to a solution only nicely for a convex function, right? However, in practice, gradient descent is used for both convex and non-convex functions, right? So for example, if I had some function that looked like this, okay? And I ran gradient descent on this. If I started here, I have this problem of I might get stuck in the local minimum here. And that might be bad. But it still might not be terrible, right? It might be a pretty decent solution. And so even if I might not provably get to the global minimum, you can still run gradient descent for a non-convex problem. You can still have it converge to something. You just don't know if that's the global minimum or not, right? And sometimes you might get lucky. If this was your initial condition, you might actually converge exactly to your actual minimum. So gradient descent applies to all different kinds of problems. It's used in all different kinds of lost landscapes. But we will prove that for some types of convex functions under certain conditions, you can provably get to the minimum. Okay? More on your homework. See you next class.